Hello everyone, and welcome back to our journey in ordinary differential equations. Today we're going to introduce and discuss in detail a nice big family of ordinary differential equations, both linear and nonlinear, that you can solve assuming that it has a particular structure. Differential equations of this particular structure are known as homogeneous symmetric ordinary differential equations. So let's bring back a couple bits of terminology that we introduced a few videos ago, in particular homogeneous and non-homogeneous functions. So to start, a function f has a homogeneity of degree alpha if we replace our variable x with cx, and that c can factor out of our entire function and be raised to some arbitrary real number alpha times the original function f of x. Or if it's a multivariable function and we replace each of our variables x1 through xn with cxk, again, C alpha will be factored out of the entire thing with our original function left over once we factor. So here we have our single variable version and then our multi-variable version here. At least for today, we're just going to be focusing on our two variable x1, x2, aka xy type of functions, at least for today. We'll talk about the higher dimensional ones a little bit later. And keep in mind this relation, whether it be single variable or multivariable version, must be true for all c that is greater than 0. If there does not exist this particular type of decomposition when we replace our variables x with cx, then we say that that function is a non-homogeneous function. Otherwise, we call functions that have this particular structure homogeneous functions, right? Which are a good thing. So, now that we know the difference between a homogeneous and a non-homogeneous function, some people will also call it a inhomogeneous function, now let us talk about homogeneous symmetric differential equations. Okay, so the differential equations, keep in mind for first order at least, that's going to be our primary focus, at least for the time being, until we develop a little bit more theory for first order in order to tackle the higher order differential equations, which is a beautiful discussion once we get there. Keep in mind we can always write it in the form y prime is equal to some function of xy. Every single first order differential equation, whether it be linear or nonlinear, can be written in this form. So what we're going to do is we're going to write a differential equation y prime in the following representation. So in particular, we're going to have minus mxy divided by nxy. So m and n are going to be some functions of the variables x and y, and you can write this particular differential equation in an alternative form, in particular mxy dx plus nxy dy is equal to 0. Either one is perfectly fine. They are both equivalent. All right, so let's assume that we have re-represented our function f in terms of these functions m and y with negative m on the top and n on the bottom, or if it's in a horizontal form, m dx plus n dy is equal to 0. Right? And you can sort of think about what the relevance of this 0 term is and what functions can and cannot be represented in this form. I'll let you think about that on your own. So now let us define the type of differential equation that we will study today. So suppose m and n have the same degree of homogeneity. So we're assuming that this function m and this function n are both homogeneous functions and they have the same exact degree of homogeneity. Both degree 2, both degree 7, both degree 1.2, both the same degree. So if this is the case, then we say that m dx plus n dy equals 0. This particular equation is a homogeneous symmetric ODE. Right? So that's the differential equation that we're going to be focused on solving, right? Which is actually a very big class of differential equations. So let us state the theorem that's going to guide all of our solutions. And of course, we're going to prove this theorem as well. So all homogeneous symmetric ODEs, all of them, can be transformed. So this should reminisce from, for example, Bernoulli's equation into so keep in mind Bernoulli's equation was able to be transformed into first order linear inhomogeneous ODE, but homogeneous symmetric ODEs can always be transformed into a separable, which is even more easier in fact than inhomogeneous linear ODEs, via the substitution. U is equal to y over x, which is an interesting substitution, but nonetheless, that is the substitution that's going to make all of the magic happen. So let's first off start off with a proof of this theorem, and then we'll look into a few examples for it. All right, so just like with any theorem, when we seek to prove it, we always start off by stating the things that we are assuming to be true. So we're going to assume that m and n are both homogeneous functions, and both of them are of the same degree of homogeneity. Let us assume that number is of course a real number, and then we're going to consider the differential equation m dx plus n dy is equal to 0. And our goal is to prove that this differential equation can always be represented as a separable differential equation, and we've already proven that separable differential equations can always be solved with basic integration techniques. All right, so now we've set the stage for our proof. Let us see if we can build something from it. So if m and n are both homogeneous functions, then if we replace xy with, for example, mcx and mcy, then this will be equal to c alpha times mxy, and also n cx times cy will be equal to c alpha n xy. And these are both, since m and n are homogeneous functions, both a degree alpha. And keep in mind this is going to be true for every c greater than 0. All right? So if both of these equations are true, what we can do is we can divide these equations by one another. And keep in mind, c is greater than 0, that means c alpha is a positive number as well. Therefore, we can divide both sides by c alpha, for example. So once we do that, we're going to have, from the right-hand side, mxy divided by nxy, and on the left-hand side, we're going to have mcx cy all over ncx cy. And keep in mind, this is also going to be true for all c greater than 0. Okay, so if that is the case, what we're going to do is we're going to let c be equal to 1 over x for x greater than 0. Once we do this, keep in mind that cx will turn into cx, which is going to be equal to 1, and cyb will turn into 1 over x times y, which is equal to y over x. And there's our magic little y over x substitution that we're eventually going to use for our substitution for our original differential equation. So once we have that, we're going to have that mxy over nxy can always be represented in the form m1 y over x n1 y over x. So this quotient always is true, right? So let's call this equation star because we're going to come back and use this relation in just a moment. All right, so let's go back to our original differential equation, which was, keep in mind, mxy dx plus nxy dy is equal to 0. And let's divide both sides of this equation by, what do I want to do? Let's actually divide both sides of this equation by dx so I can get that y prime term going. So once I have this, I'm going to have nxy times dy over dx plus mxy is equal to 0, right? And keep in mind this is the original differential equation, and now we're going to use the substitution. Let u be equal to y over x, and let us assume that x is greater than 0 for our domain. So if u is equal to y over x, then y is going to be equal to u times x, and then we can figure out, okay, well, what would dy over dx be equal to in this new coordinate system? So if y is equal to ux, that means y prime is equal to first times the derivative of the second, which is just 1. So first derivative of second plus second times the derivative of the first. So that gives us this particular substitution as well. All right, so once we have our representation for y and our representation for y prime, then we can substitute and hope this comes out to a separable differential equation. So we're going to have nxy times dy over dx, which is u plus x times du over dx, plus mxy is equal to 0. And now what I want to do is let's subtract m from both sides, and then I want to divide both sides by n, right? And once I divide by n, then I'm going to subtract u, and I'll leave that x du dx term by itself. So I'm just going to solve for x times du over dx. So once I have that, I'm going to have x times du over dx is equal to minus mxy over nxy. Now that should look very, very familiar. Minus u. And keep in mind, this expression, mxy over nxy, can always be represented in another way. In particular, du over dx can always be represented as minus 1 times m1 y over x over n1 y over x from that previous little lemma that we did at the beginning of this proof. And keep in mind that y over x is just another way of saying u. So what do we have? So this is going to be x times du over dx is equal to minus 1 times m 1 comma u n 1 comma u minus u, right? So what variable do you see on the right-hand side of this expression? This is just a function of u. This is just a function of u of x in particular. So that's actually very nice. So let's give this function a name. Let's call it g of x. Let's give it a name. So what we have here is x times du over dx is equal to just some function of x. Actually, it's a function of u. So let's just call it g of u, right? So what does that mean? So from here, we have what? So I can actually multiply both sides of this equation by dx and then divide by x. So I'm going to have du over gu is equal to dx over x. And what type of equation is this? This is a separable ordinary differential equation, right? So from here, we're going to have some relation, I guess, because keep in mind g of u probably is not necessarily invertible or a one-to-one relation, so we shouldn't expect that we can get like, u is equal to some function of x and go backwards, right? But let's assume that we have that u is equal to some relation of x. It might not be a one-to-one relation, it could be a multivariate one. We don't necessarily know, nor do we care, right? But keep in mind, u is just a fancy way of saying y over x, and then we just need to solve that equation for y, and then we're going to have y is equal to some potentially multivariate relation of x times some function of x, which is the solution to the original homogeneous symmetric ordinary differential equation. But of course, this proof stops at this particular line because the only thing we aimed to solve was to show that that original homogeneous symmetric differential equation can always be transformed into a separable one, which we have gone ahead and proved. Now let us work through a numerical example just to make sure we understand the theory behind this method. Let's consider this particular example, which isn't actually too difficult, but I just want to choose this particular example just to sort of illustrate how this method works. So to sort of get some idea of what we're looking at here, this is obviously a first order differential equation with a nonlinear term, and you should be able to also identify this as a Bernoulli equation with n is equal to 2. But let us assume that we do not want to use Bernoulli's approach, and let's assume that maybe it's too complicated or maybe it creates some complications that we don't really want to deal with algebraically. So let's see how this homogeneous symmetric ODE approach actually solves these problems. So the first thing that I want to do is write it in the representation, in particular m dx plus n dy is equal to 0, or something equivalent to it. Right. So what we're going to have is we're going to have, for example, x squared, and then we're going to have dy. So we're going to multiply both sides of the equation by dx, and then we're going to have plus minus 3xy minus 2y squared times dx, and that's all going to be equal to 0. All right, so the first thing I'm going to do is I'm just going to call this m. You could call it n if you really want to. And then I'm just going to call this function here, I'm going to call this n. You can call it m if you want to, just stay consistent with everything. So the first thing that we need to verify is that both of these functions are homogeneous functions, and the degree of homogeneity, if they are homogeneous, are equal to one another. Right? So if we do mcx cy, that's going to be equal to cx to the power of 2, which is the same as c squared times x squared, which is the same as c squared times xy. So the degree of homogeneity for function m is equal to 2. Similarly, ncx cy is going to be equal to minus 3 cx cy minus 2 cy squared, which would be equal to c squared times minus 3xy minus 2y squared, which is the same thing as m. So it's c squared times nxy, which implies that the degree of homogeneity for n is equal to 2. And since these two match, that means this is a homogeneous symmetric differential equation. So this is a homogeneous symmetric ordinary differential equation, in particular a nonlinear one. Okay, so that's wonderful. So, since it's a homogeneous symmetric ordinary differential equation, that means the substitution u is equal to y over x will transform this into a separable differential equation. So, if u is equal to y over x, that means y is equal to u times x, which means that y prime is equal to u plus xu prime. Right? So if we switch back into our original expression, so x squared times y prime, u plus xu prime, minus 3x times y, and keep in mind y is equal to ux, was equal to 2y squared. And then we can, for example, distribute everything. Actually, yeah, let's distribute and see what we have here. Actually, let's keep this first term as it is. And then over here, we're going to have 3u times x squared. And over here, we're going to have, what do we have on that right-hand side? 2u squared times x squared. And notice what we have here. We have a common x squared term. That's actually always going to be the case for these types of equations. So what we have here is what? So we're going to have u plus xu prime minus 3u is equal to 2u squared. So this is the differential equation in terms of u, so it's still nonlinear. Hopefully it's an easier equation than what we started with. So what do we have? So we have u minus 3u, so it's going to be equal to xu prime minus 2u is equal to 2u squared. And what we can do is add 2u to both sides. So we're going to have x times du over dx is equal to 2u squared minus 2u, which is the same as 2 times u squared minus u, which we're going to factor in just a moment. Multiply both sides by dx, divide both sides by x, and divide both sides by that u term, and we're going to have du over u times u minus 1 is equal to, let's keep that 2 on the right-hand side just to not have any constants on the bottom, sometimes easy to forget. And we're going to have 2 over x dx. And then we're going to integrate. Right? So once we have this, then how are we going to solve this particular differential equation? So we have a factored rational expression, so we can use partial fraction decomposition on that denominator. So we're going to have, for example, the integral of a divided by u plus b divided by u minus 1 for some constants a and b, for which are going to be determined in just a moment. On the right hand side, we're going to have 2 times the natural log of x plus some constant c. We don't necessarily need this absolute value here because we're assuming that x is typically bigger than 0 for this particular approach. So first off, let's figure out what is this a and this b. So if this expression is equal to this expression, excluding the du term, we're going to have 1 is equal to a times u plus 1 plus b times u. So when u is equal to 0, we can clearly see that a must be equal to 1, because we're going to have a times 1 is equal to 1, so that's obvious. And if u is equal to minus 1, we can clearly see that b is going to be equal to minus 1, because we're going to have b times minus 1 is equal to 1, so that means b must be the opposite of 1. Right? So once we have that, that means we can rewrite our partial fraction decomposition. In particular, we're going to have 1 times the natural log of u minus 1 times the natural log of u plus 1. Wait, it should be plus 1, should it not? Let's go back and make sure. I believe it was plus. Yeah, there should be a plus there, right? Because it was minus on the left-hand side, so it should be plus. I'm glad I caught that now. There we go. All fixed. So once we have that, I sort of corrected myself, kind of funny. So we have the natural log of u plus 1, and that's going to be equal to 2 times the natural log of x, or the natural log of x squared, plus some arbitrary constant c. On the left, we can probably use some rules for natural logarithms. In particular, the natural log of u over u plus 1 is equal to some constant plus the natural log of x squared, and then we can just exponentiate this particular expression, cancel out the e and ln, and then define, for example, e to the c to be equal to some arbitrary constant k there. Right. So once we have that, then we can write our solution as u over u plus 1 is equal to some constant k times x squared. So that is our implicit solution in terms of u. But we didn't start with a equation u. Remember, we used the substitution, u is equal to y over x, so we need to switch back and write our solution in terms of y. So we're going to have y over x plus 1 is equal to k times x squared. Let's multiply top and bottom by x to get rid of those nasty fractions, and then we're going to have y all over x plus y is equal to kx squared, and that is going to be our implicit solution for the original homogeneous symmetric ordinary differential equation. And if you want to practice your Bernoulli equation substitutions, you should be able to get the same exact solution. So that is how you can solve homogeneous symmetric ordinary differential equations, which is a good approach for several nonlinear equations. Hope you enjoyed this video, and I'll see you in the next one. Take care.